equation and seeing central space differencing explodes, first order upwind works. And now the question is why and how. What we are seeking now is what we call modified equation of our problem. And I'll see if I can do both the central space and the upwind in the same process. Now let's write it on the form, the discrete form directly, with the n over delta t plus a 0, and then the first order derivative, which now was for central scheme j plus 1 minus j minus 1 divided by 2 delta x. And then I do it like this. The first order upwind, then the last term looks like a 0 uj n minus uj minus 1 n divided by one single delta x. So there you have both variants for the last term, and then of course equal to 0. It's missing. Finding the modified equation, that's a long walk. You start by investigating the consistency. Are these schemes consistent? Meaning, are you actually solving the correct equation? And the equation we would like to solve is time derivative plus a 0 x derivative equal to 0. Just written in the form sub meanings derivative. How do you check if that scheme is consistent? Well, that's the same as also checking what's the order of these two schemes. Well, you insert the Taylor series. We are going to need the Taylor series in time, which then equals n, and then delta t. And now we have to start using some symbols for different derivatives. Well, we can use this script for time derivative. Delta t times time derivative, and next term, delta t square half u double derivative, and higher order terms. Then we are going to need un j, both plus and minus 1. We're going to need the plus 1 series here, and the minus 1, and the minus 1. So I write both series here as plus and minus. Taylor expanded, you have the center point, ujn, and then plus or minus delta x, and now space derivative, plus, and then delta x square, half, u double, and then plus minus delta x 3 over 6, u1, 2, 3, and then higher order terms. I'm not certain how many terms we need. We'll see when we start to insert them. Let's try the central space first and see what happens. For the time term, we insert the time series here. So what do you get? You subtract the center point. When you insert the series, he will disappear. So this will be what is left. We will have 1 over delta t multiplied with the first term that comes alive is delta t times ut. That looks promising actually. Remember, you should get back your original differential equation, or else you've done something wrong, then it's inconsistent. But also I get this term. So that should now read something like plus delta t squared and halved, and then double derivative, and then higher order terms. That was time derivative. Plus, then comes a 0 over 2 times delta x, and then what we get here. Here, in the central scheme, I have the difference between j plus 1 and j minus 1. So I should take the positive series minus the negative series. What do you get? Well, the center point will disappear. This one will survive. I will have plus the first one minus the second one, so I will have 2 of him. 2 delta x u x. Also looks very promising. Term number 3, he will disappear. Plus the first one, but then I'll have minus from the other series, since it's a minus in between them, so he will disappear. But this one will survive. I will have 2 of him, plus 2 times delta x to the power of 3 over 6, u 1, 2, 3, and then higher order terms. What will we end up with? Well, delta t falls, so I'm left with ut there. Next term will look something like this, delta t half, double derivative, and then even higher order terms. Here, 2 delta x falls, so I will have plus a 0, write it like this, ux, and here, well, the 2 falls and one of these delta x's falls, so I will have a delta x squared, 6 ux x x, and then plus even higher order terms equal to 0. So from this equation we can now say, yes, this scheme is consistent because let all the deltas go to 0 and you are back where we started. Yes, it is consistent. Also, you can say the adder, the biggest adder terms will be first order in space, in time, and second order in space. So this is exactly everything as it should be. Everybody with me so far? That's okay? Do the same now with the first order upwind. We have this version. Well, the time will be exactly the same, so we don't have to worry about that. But we will have something different with the spatial. Now let's see, I don't have a 2 there. I will have plus a 0 divided by one single delta x, and then multiplied with uj, the center point, minus the Taylor series, the negative Taylor series. Okay, uj, he will fall. And then I will have, here it says minus this one, but then I have a minus there already, so yes, I will get something like delta x ux, which actually is okay. This is what I want. But then, term number 3, he also survives. He's positive here, but he's negative there, so I will have minus this one, delta x half, squared and half, and then uxx, and then even higher order terms. So here is something different from the central scheme. So what do we get here? Well, when you insert delta t, you get the same again, but here we will now get plus a0 multiplying with u delta x falls, so this will only be ux, plus, sorry, not plus, it will be minus delta x squared half uxx, and then higher order terms as well. Again, we can say yes, this scheme is consistent. The first order upwind scheme is consistent. When the deltas, that was wrong, shouldn't be square, you divide by one of them. When the delta go to 0, you get back the original equation as you should. Yes, it is consistent. The order, still first order in time, but now also first order in space. So we have lost one order of accuracy here by the first order upwind scheme. In the book by Felsiger, you will actually stop here and call these two variants for the modified equation. I'm not totally agreeing with him. We should continue this a little bit further. I want to get rid of this term here from the equation. I don't want to have a mix between time derivatives and space derivatives here. I want to get rid of that term. How should I get rid of it? Well, you take this equation that we have at the bottom. What should we call it? Equation number star, for instance. Just the star. And if I now create or modify that one a little bit, take minus delta t half, and then take the time derivative of the entire equation, ddt of this equation star. What will he look like? Well, the first term, the time derivative term alone, he will now look something like this. He will look like minus delta t half, and then I will have u double derivative with respect to time. This one. He will be now this term, which is what I can use to get rid of him in the next step. But I have to take the time derivative of the rest here. So what else do I get? I get a time derivative of him. That's not important, so I skip him. But here I will have something strange. Time derivative of him. What will he be? Well, he will now look something like minus, and then delta t multiplied with a0 half here and here. And then I have a mixed derivative, u t x. That was unfortunate, but no choice. We will get the same here in this first order upwind version, exactly the same. And then I will have even other terms as well, but they will be of higher order. Here it will be u t x x. Here it will be u t x x x. Still so high order that I don't care about them. But these two, they are a problem. So if I now take my original equations, these star equations, and subtract the one I have created here, I will get rid of the term here that I wanted to get rid of, yes, but then I have created another one, which I also doesn't want to have. I don't like this guy, tx. Let's get rid of him. How can we get rid of him? Well, now we create another operator. It must be positive, and it must have the term delta t a0 half in front of him, and now I need a mixed derivative. Again, I sort of create it by looking at the first term, just the first order time derivative, meaning I have to take the space derivative of the entire equation. What do I get then? Well, I get what I want. Here I will now have a term reading plus delta t a0 half, and now this mixed derivative. What else do I get? Well, I will get something from him. And I get the same here as well. What will he look like? Well, he will be plus, and it will be a delta t, and it will be a 0 half multiplied with a 0, goes for both of them. So here is squared, and then u x x. Everybody with me so far? Rather manipulative, if you say the least. Of course, you don't do this by hand. Fire up Maple, tailor insert, then he does it for you. But okay, this is so simple, it should be possible to see here. Okay, what will I have now in the end? Let's see, I can get rid of him at least. I think I don't need anything else. I will have even higher order terms here as well, which I don't care about. Now take the sum of these three equations. Our original equations, the two versions of the star, then you will have minus him and plus him. What will you get? Well, this term, he will survive as he should. So I will have, not a, sorry, u time derivative. That was the first term. That's nice. Then I will have this term. I take that one first. Plus a0 u x. Of course, that goes for both versions, so that's okay. And this is, of course, what we should have, getting the original equation back. Now, what else do we get? Well, we will have from him, he was falling out from him, and then we added something here, which we then got rid of here, but then we got this one instead. So we get this term. He is added. Now I have, well, not easy to see. Let's write him in. He should then read plus, he falls, yeah, so it should be delta t a0 squared half uxx directly. That was then caused by him, and then the double step we had to do, these two equations. What else do we have? I have some third order terms here. Don't care about that. I have a term here, but that one only belongs to the upwind version. So I write him here as well. He's negative, so I say minus. What should we call him? A0 delta x half uxx upwind version. That's only for the upwind, okay? And this equals higher order terms. Okay, now I can get rid of this, I think. No questions so far? It's okay? We write the equation like this. Time derivative plus a0 base derivative equals, and then throw these terms on the other side. What will it be? This one will become negative, minus delta t a0 squared half. This one becomes positive, plus a0 delta x half multiplied with uxx. This one was from the upwind scheme only. Upwind. For the central space scheme, we didn't have any other terms here. And then even higher order terms. And now we can actually see what's going on. This is what I would call the modified equation. Get rid of unnecessary time derivatives, terms that's not part of the original equation. Get rid of these by manipulating a little algebraic tricks. Then it's possible. Yes. So now you see what's actually going on here. Double derivative. This is the diffusion. And our original equation, it doesn't have that. No diffusion. Okay. Pure central space discretization, you have a negative diffusion. It's going to blow up unconditionally. Negative diffusion, he doesn't damp down any gradients, he enhances them, he increases them. So yes, any changes from zero, he will blow up. Negative diffusion. This one is also part of the upwind scheme. There's also some negative diffusion there. So I will call him numerical diffusion. Numerical diffusion, which is then smaller than zero, which is a very bad idea, so we don't like that. This one, that's only for the upwind scheme. He's positive. So that's diffusion that is added on purpose when you choose the upwind scheme. So I call this one artificial. Artificial diffusion. And he's positive, so he should calm down the circuit. So to get it correct, to get it stable, we could now say the sum of these two has to be zero. Then we would have the correct solution. So what will happen if we say, okay, this one should be zero? Well, yeah, we can do that. What happens? We can do it here. This bracket in front of the double derivative here should be zero. 1/2 go outside and 1a0 goes outside. What are we left with? Well, we are left with minus delta t multiplied with a0 plus delta x has to be 0, which is the same as CFL equals to 1. So that's the CFL criteria again. So yeah, just for this example, the advection equation, you can get rid of all diffusion by choosing delta t so that you get the Coulomb-Friedrich-Levy condition equal to 1 directly. Yes, then it will be okay. As you saw from the demonstration, if I chose a big delta t, so CFL became 1, then he disappears. Then it's okay. And here you see the reason why. So using the modified equation will give you a lot of information. Can be a tough way to get it, even for like this one, fairly simple partial differential equation. Try to do this with the Navier-Stokes. You're going to need a lot of paper, or Maple is going to have a tough job. So I don't think it's possible, not for a nonlinear equation, to do this. And also in the end, hard to get any information, understandable information out of it. But for model equations, simple equations, yes, this is a beautiful tool that we have. And also along the way, we check the scheme for consistency, we check the scheme for order. So yes, this is going to be something you find on the exam, of course. So I demand that you are able to do this all the way to what I will call a modified equation. Any questions to this one? Very simple, very easy. That's good. yeah, well, we're here. Next Wednesday, we are thrown out of this room. We can't use it. They have a meeting here, some secretaries, very important stuff, so we have to move. But I found F4, that's in the physics building. So that one is fairly okay for us. So we use F4 next Wednesday. Okay? I think it should be okay that we're here. For this upwind version that we had here, yes, it was stable as long as you were within the CFL limits. CFL should be between 0 and 1. And as I said here, what we actually are doing then is to take our hyperbolic equation and then we add some viscosity into the problem, creating something that is now a parabolic equation system. And that's why also you see this smearing out of gradients using the first order upwind schemes. This will also be the case for even higher order upwind schemes. They will do the same, but not to the same amount. I think you have some demonstration of them. Let's see. Yeah, it's the finite difference number 6, where they are looking into the square cavity problem. Here, the top wall is moving to the left. So you get the main vortex here, secondary down in the corners, and the Reynolds number here is so big that you get the third one up here, very small one. For this simulation, they have used central space differencing. So we said FTCS scheme. And the correct value for the stream function here in the center, the maximum stream function, should be 0.1. A little bit above 0.1. So he is fairly close to the truth. Version B, they have created a hybrid scheme. They use 80% of the central scheme plus 20% of the first order upwind scheme. So it's a hybrid. You mix it. That's possible. And you get the same flow pattern, fairly decent. But look at the size of the stream function. So you add viscosity into the problem. And I think the last one here is even worse. Oh, sorry, the B, that was only 10% upwind. But the last one, that's 80% upwind. Still the same flow pattern, but now the stream function value is reduced by 1/3 or something. So yes, it's stable, but the result is nothing you should believe. Conclusion, never ever use first order upwind. Still a lot of CFD codes, you use it because it's so stable. So it stabilizes a lot. You can use a big delta T. It doesn't explode, but you get very strange results. And the second one, we'll take this one. That's an old comparison. That's a couple of fins did between Fluent and FeedUp. And the test case they found, that was quite nice actually. You take a quite narrow cavity, so the geometry here is very nice, and then you say you have a temperature difference on each side. And then you use this trick, Boussinesque, by saying hot air is going to be light, so the density is a little bit smaller. But you still simulate this incompressible, but you just use this expansion coefficient beta based on the temperature. That would now be a buoyancy force for hot air. And And then on the other side is cold, so there the air should be chilled down. The density then is higher, so he should fall down. So, and also top and bottom, you say normal derivative equal to 0. So if the driving force here is not too strong, you should have hot air going up, making the turn, and then be cold and fall down again. One big, long vortex. The driving force in this problem is called a Grashof number. And then, for this problem, if the Grashof number is small, yes, then you will have this nice one long vortex, very elongated. And there also you will have an analytical solution from wall to wall, given by Bachelor. Very nice solution. Temperature will go linear, velocity profile will go like x to the power of 3. Very nice velocity profile. But to achieve it, you need a Grashof number smaller than, I think it was 10,000. That was the critical one. Yeah. Grashof number 10,000, that's the limit. If you are below that, the driving force is not so strong, you should get the Bachelor solution. Straight temperature profile and this nice velocity profile. If you have a higher Grashof number, more than 10,000, what's going to happen then? Well, this elongated long vortex is going to break up into many small ones. So then you will have some alternating vortices all the way down. It's not turbulent, still laminar flow, but you don't have one big one, you have many small ones instead. And this is something you can do in the lab and see, yes, this is going to happen. Of course, with even higher driving force, even higher Grashof numbers, then you can make it turbulent. That's a different story. So here they did a test case, two codes. They use an old version of Fluent. And in those days, Fluent were based on finite difference. Now it's finite volume. And they compared it with a feed up, that was a finite element code. And also in those days, the old Fluent code used, of course, first order Rockwing scheme, because it was so stable and nice. Feed up, finite element, he didn't. He did it more correct. And then they played around with the Grashof numbers, and they did two cases. 8,500, that should be stable, and then close to 15,000. Then the solution should break up into many small vortices. So for the first case, Grashof number 8,500, both codes produced this velocity profile. Here the cavity is tilted 90 degrees, so you actually see the velocities up here. That's on the top. So yes, you have one big vortex going here, and then turn, go back, and then go negative here. Just one vortex, as you should. And both programs agree fairly well. But for 15,000, it's quite embarrassing for Fluent actually. He got this one. He smeared out everything and got one big vortex and claims that this is the solution. This was the feed up solution, and this one is correct. You get alternating vortices. So it's quite possible with an upstream code to smear out the entire physics. You don't see it anymore. And if you think of it, as we had it here with the modified equation, you think you are simulating Reynolds number 100, but actually you are simulating Reynolds number 10 or 1. So you are simulating a different fluid than you thought you did. Very dangerous, of course. So this is really something you have to be aware of. Nowadays, of course, the Fluent salesman, he would start screaming if you saw this. Now Fluent is based on finite volume and is much better. I have tested it. It could be fun to do it. It's a fairly easy setup for a test case. Okay. as a demonstration. So again, conclusion: never use it. Sometimes you have to, but if you have to, then don't tell anybody. It's a nasty one. Okay, any questions to that one? Let's see, we can take a quick break. I have to leave a little bit before 4. We have an exercise in the basic course I have to start up, so let's take a 10-minute break.